Welcome to the fourth lecture of the mini course in a dynamical system approach for Lane-Emden type problems. We're going to see in details the existence and properties of the regular solutions for Pucci's operator. Let us consider the following initial value problem for Pucci's operator, derived, as you saw in the previous lectures, as u2 prime m plus minus of this expression, where inside the expression there is also a small m plus minus depending on the sign of u prime. U of 0 is gamma for a regular solution, u prime of 0 is 0 and gamma positive. The m plus minus large M and small m are given by these functions as straight lines with slope small lambda, big lambda, and for large M, S over small lambda, S over big lambda for S negative or 0 and as positive respectively. The same definitions hold similar definitions for m minus m minus. So let's see what a regular solution is. For us, the regular solution, by a regular solution, we mean a u, which is twice differentiable for r positive and is C1 up to the origin. Under this definition, since the solution is a radial solution, we obtain for p plus and p minus that u prime at 0 is 0 because it's reflected in the vertical line and it has to match with C1 differentiability. What are the properties of these regular solutions? Rp is going to be a number, positive number or plus infinity, denoting the radius of maximal interval where u is positive. U is a solution of Pucci plus or Pucci minus if R P is plus infinity, then U corresponds to a radial positive solution in the whole Rn. If Rp is finite, it gives a solution with the Dirichlet boundary conditions in the ball so that U is equal to 0 on the boundary of the ball. A regular positive solution UP in the intervals 0 RP, satisfying U of 0 is gamma for some gamma positive, can be rescaled in the following way. V of R is going to be tau U, tau to the power 1 over alpha R, for alpha equals to 2 plus A divided by P minus 1, and tau a scaling argument positive. And this is still a positive solution of the same equation, but in a different radius. It's just to perform calculations and see. Also, the height of the solution at 0 changes by this scaling term. So it becomes tau gamma. If U is defined in the whole interval, then you have a family of regular solutions obtained via rescaling, because the infinity is rescaled to infinity. In this case, we say that U is unique up to scaling. A solution in the ball of radius Rp automatically produces a solution in an arbitrary ball by properly choosing this parameter tau, which changes the radius. So if you have a solution in a ball, you obtain by rescaling a solution in a ball with a different radius. A definition given previously on regular solutions, depending on their decay, was a solution of Pucci plus and Pucci minus, and alpha given by 2 plus A over P minus 1 for the Pucci weighted operator, is said to be fast decaying if it decays as r goes to infinity as r to the minus n tilde minus 2, where n tilde is either n tilde plus or n tilde minus, depending on the operator. Slow decaying was defined as a solution which decays as r goes to plus infinity, like r to the power minus alpha. And pseudo-slow decaying solutions, those which decay in a strip of rate of decay r to the minus alpha. By rescaling a fast decaying solution, we get infinitely many constant decaying solutions which give a different value for the constant C, and infinitely many fast decaying solutions. The same happens for the slow decaying, for the blowing up solutions at r equal to 0. Then we can go back to the dynamical system associated to the Pucci's equation and see how we can identify regular solutions in the dynamical systems. And this is given by this theorem. If we have the dynamical system in the first quadrant, as we have seen in the other lectures, then the theorem says, let U equals to UP be a positive regular solution of Pucci plus or Pucci minus, then the corresponding trajectory belongs to the first quadrant and is the unique trajectory of the dynamical system which exits from N0. So at minus infinity, it arrives at N0. In terms of the pictures, for example, if P is bigger than PSA and P is, and M is the Pucci plus, for example, we could have a flow for which the trajectory that is coming out of N0 is this red trajectory, which exits a box around N0 and A0. As it exits this ball, we're going to see that it blows up in finite time, given that U is 0 at a finite radius. So we get a solution in a ball corresponding to this type of trajectory exiting N0. On the other hand, if you take P equals to PA star, which is the critical exponent for the weighted Pucci operator, this trajectory that comes out of N0, exits N0, and arrives at A0 in plus infinite time, is going to correspond to the regular solution, fast decaying solutions, as in this red profile. So we are proving now that they correspond one-to-one like this, and that the regular solution is the one that exits N0. How do we prove this? The proof is the same for both operators, so let's take M plus Pucci plus operator. The solution UP satisfies, since it's regular, as R goes to 0, UR goes to U0, which is gamma, and the derivative as R goes to 0 approaches, or the limit is U prime at 0, which is 0 for a regular solution. Therefore, if you take the expression that defines the x variable, it's U prime divided by gamma. So this is going to the limit of x to the t as t goes to minus infinity is 0. So any regular solution will have a trajectory that in the horizontal lines is approaching the origin. Let's see what happens to the z variable for a trajectory associated to the regular solution. It depends on A. In case A is equal to 0, the non-weighted Pucci's problem, we have the limit of z to the t as t goes to minus infinity is going to be the limit of the expression of z of t, but this gives, this goes to gamma, so this goes to gamma to the p, and then you have this quotient, and this quotient is going to be exactly u2 prime at 0. But u2 prime at 0 is a negative number for a regular solution exceeding 0. So this is a number to which z is going to approach as t goes to minus infinity. Therefore, it's a point in the vertical line with x equals to 0 and z0 given by this number. If A is different from 0, the case we are studying the weighted problem, then we have to go in a different direction with a different argument to see that z of t approaches a number, has a finite limit as t goes to minus infinity. First, let us show that there is a radius such that u prime is different from 0 in the whole interval 0, r1, this radius. If this was not true, then there would be a sequence of positive radii, Rn, going to 0, such that the derivative at this radii are all 0. By the mean value theorem, this yields the existence of another sequence in between these 2 points, such that the second derivative is 0. Thus, since u prime cannot be identically 0 in the neighborhood of 0 by the equations of Pucci plus operator, then u changes infinitely many times its concavity in the neighborhood of 0, because this is saying this is changing concavity. In terms of the dynamical systems for Pucci plus, for example, this means that the respective trajectory intersect the line L plus, which is the line where the derivative is 0, more than once as t goes to minus infinity. In particular, it should pass from region plus to region minus infinitely many times, which by the flow may only occur when x of these points are above 1 plus a over p, for a bigger than 1. But this contradicts the fact that x of these Rn's are going to 0, therefore x of Sn's are also going to 0 for large N, because x of t is going to 0 as t goes to minus infinity. Therefore, u prime different from 0 for all r's close to 0, so in an interval of 0, and we have that zt is well defined in some interval minus infinity t hat, because this is different from 0, so that the a priori bounds yield that zt is less than lambda n plus a for t less than t hat, because they are well defined and they are real numbers. And as you take the limit, this is going to be a finite number. Moreover, it could be that z is 0. Z of minus infinity is 0. But why it's not? Because 0 is a stationary point. Let's say it's a point where the unstable manifold at 0 is in the vertical line. So each time an orbit approaches 0, it's pushed up by the unstable manifold at 0 in the vertical line. So it cannot correspond to a solution U in the interval 0R. Hence, it converges to the only point that is stationary in the vertical line, which is N0, independently of the initial datum gamma positive. So that's how we prove that a regular solution has to exit from N0 in minus infinity time. Here are some pictures of this fact. Regular solutions, for example, exiting N0 and going to A0, which is going to correspond to a fast decaying regular solution, or a trajectory exiting from N0 and going out of a box around here. And this says that for a finite time, there is blow up in the x variable, which means that this is a regular solution in the ball. There is a radius where u is 0 because u is in the denominator of the definition of x. A remark, thus local uniqueness. By local uniqueness, one concludes that a regular solution UP corresponds to the unique trajectory gamma p exiting N0 for p bigger than 1. Here, gamma p is defined in the maximal interval 0 TP. TP could be plus infinity, so it's a solution in the whole Rn, or TP could be finite and then it's a solution in the ball. But then we have the correspondence of the regular solutions with trajectories exiting N0. Another remark, the fact that gamma p does not depend on the initial datum of UP is not a surprise, since we already observed that the change of initial datum is equivalent to rescaling of the radius. This in turn is equivalent to shifting the time for the system XZ, which does not produce any change in the trajectories since it's an autonomous system. So we are going to see the same trajectory when we look at the phase plane XZ, even when we do rescalings. So we can talk about subintervals of P. Given an exponent P for the nonlinear term in the Pucci equation, for a regular solution UP of Pucci plus or Pucci minus, which is positive in 0 plus infinity, holds according to its behavior at infinity. Taking into account that UP is unique up to rescaling, we define the following sets. So we subdivide the P's by the type of decay the UP solutions have. We denote by F the intervals of P such that UP is fast decaying. By S, the intervals of P parameters for which UP is slow decaying, and P, the interval of P parameters for which UP is pseudo-slow decaying. Other than this, there are regular solutions in the ball. So we call the intervals of P's such that the Pucci plus and minus has a solution in the ball by C. Therefore, these are all possibilities for parameters P in regular solutions. Are these the radius of maximum positivity interval for UP? So if you consider the trajectory gamma P, xt, zt associated to a regular solution, so it's exiting from N0, you can split the interval of P parameters 1 plus infinity as a disjoint union of C, F, P, and S. Another remark, if P is in C, the trajectory gamma P crosses the line X in tilde plus minus 2. So it exits the box and the next blows up in finite time. This property is preserved by P's close to P. Why? Because the trajectories satisfy the dynamical system, the ODEs, and by continuity of the parameters, if for P there is blow up in finite time, for other P's close to P, there is going to be blow up in finite time too, because of the ODE theory. This is a picture of different regular solutions for Pucci plus operator, exiting from N0, a trajectory that arrives at A0 is going to be a fast decaying solution, so this P is going to be in the F subset. This one coming from N0 and going out of a box is going to correspond to a solution in the ball. So this is going to be for P's less than P star. This that exits from N0 is a regular solution that goes around a periodic orbit, is going to be associated to a pseudo-slow decaying regular solution. And the one that arrives at A0, which is fast decaying, is a fast decaying in the exterior of a ball. And there are, for example, regular solutions exiting N0 and going out of these a priori bounds, let's say, blowing up in finite time, corresponding to a solution in the ball. When P, for example, is equal to PSA, which is this case, and when P is less than PSA. So solutions, regular solutions in the ball are seen in the dynamical systems associated to this trajectory exiting N0. Thank you for your attention and see you in the next lectures.